Security has traditionally been a static game. You place a camera, you place a fence, you place a guard. But what happens when the perimeter gets complicated? What happens when there are stairs, rubble, or walls that need to be scaled? For years, the answer was to build bigger robots or send more humans. But a team at the Swiss Federal Institute of Technology in Zurich asked a different question. What if the robot could jump? This question led to the development of a robot known simply as Ascento. While some industry observers refer to it as the Ascento Guard, the official academic title is just Ascento. It is a two-wheeled jumping robot that uses a four-bar linkage with torsional springs to move. It is designed for indoor navigation where agility is more valuable than speed. But when you strip away the marketing and look at the engineering, the trade-offs become stark. Here is the thing about jumping. It is mechanically efficient for clearing obstacles, but it is energetically expensive. A standard wheeled robot rolls over a step. It might need a ramp or a gentle incline. A jumping robot, like the Ascento, stores energy in springs and releases it to launch itself into the air. This requires a significant burst of power. If you are running on a battery, that burst drains capacity much faster than rolling does. This creates a fundamental tension in security applications. A security robot needs to patrol for hours, but jumping consumes energy in short, intense spikes. The battery density required to sustain this mode of locomotion is a major engineering hurdle. You cannot simply use a standard lithium-ion pack and expect long endurance without sacrificing payload or size. Now consider the suspension dynamics. When a robot jumps, it lands. That landing is an impact event. The four-bar linkage is designed to absorb some of this shock, but the forces involved are high. In a laboratory setting, the floor is flat and clean. In a real security scenario, the floor might be covered in debris. A single-wheeled robot can roll over small rocks. A jumping robot might catch a toe on a piece of debris and flip. The suspension system has to be robust enough to handle the landing impact, yet compliant enough to not damage the chassis or the sensitive electronics inside. This is a delicate balance. Too stiff, and the landing shocks the internal components. Too soft, and the robot cannot maintain stability for the next jump. There is also the question of control. The Ascento uses direct drive actuation, which means the motors are connected directly to the joints without gears. This allows for high-speed response, which is necessary for mid-air adjustments. But it also means the motors are constantly fighting gravity and momentum. The control algorithms are adapted from legged robots like the ANYL system. These algorithms were originally designed for walking, not for high-impact jumping. Adapting them requires significant tuning. The robot needs to know exactly when to commit to a jump. If it jumps at the wrong time, it wastes energy. If it fails to jump when needed, it stalls. This brings us to the failure modes in real-world debris scenarios. Research indicates that the single degree of freedom legs restrict complex manipulation tasks. This means the robot cannot use its legs to push things out of the way. It has to jump over them. If the obstacle is too high, the robot is stuck. If the landing zone is unstable, the robot falls. This limits its utility in disaster zones or rough environments where a security robot might be deployed. It is agile, yes, but it is not indestructible. The design prioritizes speed and clearance over durability and versatility. Furthermore, there is a confusion in the literature regarding the specific nomenclature. Some sources conflate this project with other research, such as the DIA blow robot from China, which is a 6 degree of freedom system. This conflation can lead to unrealistic expectations about what the ETH Zurich prototype can actually do. The Ascento is a compact system. It is not a heavy industrial machine. It is a proof of concept that demonstrates the viability of hybrid locomotion. It bridges the gap between static surveillance and dynamic agility. But the jump from prototype to deployable security solution is not automatic. The development highlights a trend toward commercializing academic prototypes. Moving from simulations and Weebots to real-world hardware is a massive leap. The legged robotics lab at the Swiss Federal Institute of Technology in Zurich has shown that the technology works, but the specific branding as a guard variant remains unverified in official publications. This suggests that the security application is a use case, not a product line. It is a tool for specific problems rather than a general-purpose security officer. Future security deployments may increasingly rely on hybrid wheeled-legged platforms. The ability to traverse vertical obstacles fundamentally changes the operational scope of perimeter defense. You do not need a ramp to access a rooftop if you can jump to it. You do not need a wide path if you can hop over a pile of boxes. This changes how facilities are designed for security. But the cost of that agility is paid in battery life and mechanical stress. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.